Okay, so we'll continue on the vector concept review. Okay, we'll finish that today. And if you've got time, then we've got a new topic, which is plane equations in 3D space. Okay. Okay, so let's continue on the review of vector concept here. So in the last lecture, we basically reviewed the concept of vector, and we learned, when you have a vector, there are always two basically components, okay, that you need to construct this vector. One is the length, and the other is the direction, right? And we also look at the dot product. Okay, so there are two different ways of looking at the dot product. One is just purely its mathematical definition, and the other is more or less just related to its geometric relationship, right? Okay, and the other thing that we look at is from here is we look at the projection, the idea of the vector projection. Okay. So if we have a vector A at here and a vector B at here, and we wanted to know how the A can be projected to the direction given by the B vector. Okay. So let's say we call this is A parallel vector, which is the projection here. So of course you can have another projection in this direction, right? So in the previous lecture we derived this A parallel as A dot B hat time B hat. Okay, yeah. So this one here, you're looking at the expression for the A parallel, which is the projection of A in the B direction. It has two components, right? So this one is basically the length, and this one here is basically the direction. Okay. So direction is fairly obvious because that's the direction, the B, that you wanted to project it to. And the length at here, the expression for this one here actually is quite useful. Okay, so this A dot B, okay, so this guy here, so this quantity, this is basically the projected length of A in the direction of B, right? Okay. So this A dot B hat, this is a very useful quantity. Okay, so you want a length, this is a scalar, of course. You want to project the length, and you can just simply use the vector dot that unit vector or unit vector given by this direction here. Okay, so this A dot B. Now, if you're interested, you can actually basically relate this dot product, okay, to the results we written at here. So very easy, you can prove, okay, you can actually show that this A dot B, so the dot product, right? Okay, so this dot product can be rewritten as using the expression in here, which is absolute value A parallel times absolute value of B. Okay. So you can try to show this. Okay, it's quite obvious. Okay. Yeah. If you substitute this quantity A parallel here, then you will immediately see that this A dot B will equal to this. All right. Yeah. So that's what we learned from previous lecture. Okay. Now, coming back to this diagram in here, we can clearly see what A parallel is, right? Okay. Now, often in time, you're also interested in knowing basically this quantity here. Okay. So the other direction of projection. So now we got the projection in the B. We're also interested in the projection of A in the direction that is perpendicular to the B. Okay, so that's another important. So we call this one here, let's say A perpendicular. So that's another quantity. Often in time we need that. Okay, as you can see, it's not necessarily very easy to get A perpendicular, but we can always try to obtain this A parallel first. and then get a perpendicular. Because why? Because once you get a parallel, and your a perpendicular will be simply what? Will be simply this a subtract vector a subtract the a parallel. Okay, yeah. And you will see why this is also useful, because you may need this information for further construction of a line or plane equation. Okay, so but you can't get this one easily or directly. So we get this one first, and then obtain this a perpendicular. Okay, yeah. So that's the connection in here. So this is one formula, okay, and this one here. Okay, so that we'll show you how to use this one later. Okay. Yeah. So this is pretty much about the dot product. There are a few dot product properties I listed in my lecture notes, and I don't think I'm gonna go over all the properties, but this is probably the most useful properties out here regarding dot product. Okay. Yeah. So in my lecture notes, I also listed some command how you use Maple or MATLAB commands, so you can use this command to carry out calculations or helped by MATLAB and Maple. So this is a just check it out yourself. It's quite simple. Just punch it in and enter, and you'll see how it performs. And you can just simply change the vector, and if you have a different ones, right? Now, a couple of assignments probably will ask you just to practice using MATLAB or Maple to help you with calculations. Okay. Yeah. Okay. So those are basically about dot product. No? Okay. Any questions so far? Good. Okay. So let's look at maybe the next topic now. Basically, cross product. Okay. So cross product is another very useful concept that we will actually use so much in later part of the lecture. Okay. First, for definition. So suppose we're given two vectors, let's say A and B. Okay. Then the cross product is defined as A cross B equal to absolute A, absolute B, okay, sine theta n hat. So that's the definition. The definition basically means you don't argue with that. That's what's defined. Okay, that's how basically it's defined as a cross product. Okay, yeah. So looking at this definition at here, first examination of this formula, you can clearly see there are two components at here. The first component is a bracket. And inside the bracket, it's absolute value A times absolute value B, and then times sine theta. So the theta at here is the angle between A and B, and it's the value between 0 and pi. Okay. So that would be theta. So sine theta for any angles between 0 and pi, sine theta is always a positive number. And absolute value A and absolute value B, which is the length of vector A and B, so they're also positive numbers. So the quantity inside this bracket, that essentially is a positive number. It's a scalar number, right? Yeah. And then times n hat, which is unit vector. So according to our definition of a vector, so this essentially is a length times a unit vector, right? A direction. So that what that tells you is the cross product is a vector, right? The results of a cross product is a vector, as opposed to the dot product, which is a scalar. Okay, yeah. So then what's the n hat then, right? The n hat here essentially is a unit vector, okay, perpendicular, okay, to the plane formed by A and B vector. Okay. So A and B are two vectors. Then if you draw A and B, okay, and you can easily form a plane. Okay, and it's actually a plane can be uniquely defined by these A and B vectors, right? Yeah, so it's a unique plane, right? It's not a you cannot actually form another plane given A and B like this. Okay, so well, unless A and B is the same vector, right? So but the n hat, okay, is basically a vector perpendicular to that plane. So that's what n hat is. Then obviously the cross product A and B give you a vector, right? Give you a vector, and that vector basically is perpendicular to this plane, or if you can draw the vector over here. Okay, so this is your A cross B here. Okay, so that's the idea of a cross product. So in here, see that. Often in time, you learn actually in before to determine the direction of the cross product. You use this so-called right-hand rule. Okay, so there are two ways of using right-hand rule. One way is to curve the finger, and the direction of finger curved is from A to B, and then the thumb points to the direction of this cross product. Right, that's one way for right-hand rule. And the other way right-hand rule is you use the three fingers of your right hand, and then the index finger points to A, the middle finger points to B, and then this thumb points to the results of the cross product. Right. So that's another way, basically illustrating this cross product here. Okay. Yeah. So this is a cross product. Okay, the definition of cross product here. Okay. So just to emphasize that here, so this will be the length, okay, and this will be the direction. Good. Okay. So apparently, if you want to know, so how can I obtain n hat then? And you can always obtain your n hat using A cross B and then divided by its length, right? Its length. This is a little bit sort of a contradictory. So if I want n hat, I need to know A cross B. But if I want to know A cross B, and then I have to use this, so that same doesn't work that way, right? So what we really need, I'll show you. We have another formula for A cross B. Okay. So essentially, if you're given A and B, you can use the following formula to calculate this A cross B. Okay. Yeah. Now, cross product is a very useful concept to illustrate many engineering concepts. For example, in EMAC course, okay. Probably running out of battery. Change the battery here. So, for example, in EMAC, you learn if there's a current going through, a wire, then it'll generate a magnetic field. So that's a right-hand rule, right? So you're pointing your finger to the direction of the current, then curve the finger, so that will be the direction of the the magnetic fields, right? And many other things. For example, in dynamics, and you learned if you have a particle, okay, rotating about a certain axis, okay, then you can relate, okay. You can relate the angular velocity and the linear velocity together using the cross product. So that will be an example of dynamics here, right? Yeah. You can also relate your torque, right, with the force. So you apply a force to an object, okay, and you want to know how much torque is generated with respect to certain axis. So that will be this formula. And in electrical, you can also relates this so-called Lorentz force, okay, with using this cross product. So you have a particle, charged particle traveling through a magnetic field at a certain velocity. So you can calculate this Lorentz force like this, right? And you can also calculate the so-called Laplace force, okay, using this formula. So Laplace force, essentially, if you have a wire with a current flowing through the wire, and it depends on how you orient the wire inside maybe the magnetic field, okay? So that basically will be the Laplace force. So many applications of a cross product, and later you're going to see many others, okay? Yeah. So coming back to the calculation of the cross product here, okay? This is a definition at here, so that's actually not what we mostly used for calculation. For calculating of the cross product, we use the following formula here. Okay. So let's see how do I calculate the cross product. Okay, suppose I have the two vectors a1, a2, a3 for the vector A, and the vector B, okay, b1, b2, b3. I'm sorry, yeah, I made a mistake. According to my notation, I should use half angle for vectors, right? Yeah. Okay. So if I have two vectors A and a B, then the calculation for the cross product can be, you can use the following formula. Now this formula, unfortunately, you're not going to be allowed for a formula sheet, okay, in the midterm, so you're going to have to memorize this one here. It's not particularly challenge, okay. It's just a little bit long compared to other formula. Essentially, you're calculating here is going to be a determinant of a 3x3 matrix. The first row of the matrix is ijk. If you recall from previous lecture, the symbol ijk here representing the unit vectors for the three axes of a Cartesian coordinate system, right? Okay. Now, second row here is this vector A, and the third row here is a vector B. Okay. So to calculate A cross B, you just need to calculate the determinant of this 3x3 matrix. And you can take out your first year linear algebra course to look at what's the determinant of 3x3 matrix. Well, essentially you can always start from the first row, right? If you start from the I, you cross out the first row, you look at the determinant of the remaining matrix, okay, and then times the first elements, right? And you keep going like this, okay? Yeah. So in short, and you're gonna end up with a formula, okay? First row, A2, A3, B2, B3, I hat. Okay. Yeah. Second one here, it's a minus. Okay. So technically speaking, it's a plus -1 to the power of the location of these elements, which is first row, second column, so 1 plus 2, that kind of things, right? Yeah. So I will just use a minus here. Okay. And then here is A1, A3, B1, B3, and then J hat. Last one is a plus. Okay. A1, A2, B1, B2, K hat. Okay. So that's your formula. Okay. And of course, you this is probably not the last expression. So you expand this one here to give you another one here. So which over this is a determinant. 2 by 2 determinant is easy. So this times this minus this times this, right? Okay, there. So ultimately, here is your formula for the cross product. Okay. So if you're given A and B, This is what you need to use to calculate this cross product here. I noticed a lot of a common mistake from previous year is many people make a mistake by forgetting this is actually should be a negative sign. Okay, yeah, because the danger is usually this is the first step for many other calculations following this. So if you make a mistake right here, and then typically, right, which means the rest of the calculation will be all wrong. So that's something that you have to be extra careful at here when you do that calculation, especially when you do assignments. Okay, just make sure you have a good habit by remembering there's negative here. So some people put a negative into the bracket, it will become plus sign now, but this is going to be this minus this, right? So it really depends on how you manipulate it, but otherwise it's all the same. Okay, yeah. Okay, so I'll give you ask you guys to do a quick exercise yourself at here. Okay. So here are two vectors u and v, okay, and I want you to calculate this u cross v. Okay, so time yourself. It shouldn't take you more than maybe 2 minutes to finish this kind of calculation in the actual exam setting, right? Depends on how comfortable, how much you use this formula, right? Yeah. So try it yourself. Okay, give yourself 1 or 2 minutes. So let me see who finished here. How many of you are able to finish? Okay, so good. So this will be my calculation, and here is double check with yours. Okay, yeah. So how many of you got it the same as mine? Good. All right, good. So there's no trick at it here. Just be careful with the calculation. Okay. Yeah. Then again, also in my lecture notes, I have a few properties for cross product. Okay, so take a look at these properties yourself. Okay, we don't necessarily use all the properties all the time, but it might come in handy for your other purposes. Okay, yeah. There's also MATLAB command or Maple command here in the lecture notes. Okay, and okay, so you can feel free to check it out. MATLAB seems to be very popular now. You can just simply use cross, and then it's A and B to calculate the cross product between the two vectors. Okay, yeah. For dot product, just basically dot and A and B. Okay, so A comma B. And there's another command I wanted to give it to you, but I want you to think about it because you can try it here. Remember, if you have two vectors, then inevitably you have an angle between the two vectors, right? Yeah. So you can, of course, you can hand calculate the angles of two vectors, and you can also use MATLAB to help you. So here's the command for using the MATLAB. So I want you to try yourself and also kind of try to understand what exactly does this command here do. Okay. Yeah. It's quite interesting way of calculating the angles between two vectors. Okay, so here is basically you can use MATLAB to help you. It's called. You can also use a similar command in Maple. It's called A10-2, and then norm brackets here cross AB comma dot this. So norm basically is a command calculating the magnitude of this. Okay. And then this is the cross product. This is dot product. So when you calculate the angle, you can here this formula relates this cross product and dot product together. Okay. So try it yourself and ask yourself why. Okay, and why this one works. Okay. It's actually an interesting formula you can use. So that will be part of the review now. I have two more topics for review here. Okay, so I probably can call it maybe not review, but they're quite much related to cross product, dot product. Okay. Okay. So before we get on to the equation of planes, so let's look at two more topics that are here. First one, let's look at the so-called area of a parallelogram. Okay. So what is a parallelogram? Basically, given a vector A and a vector B. Okay, so here's my vector A, here's my vector B. So you can always move the two vectors around and such that they are oriented like this, right? Okay, and they are oriented by an angle theta. Then I can use the vector A and B to form this so-called parallelogram, right? Okay, so that will be a parallelogram. And now the question here is, what will be the area of this parallelogram? Okay. So of course, we're not going to try to compute the area like the way we learned in the way we initially learned in geometry. Well, actually, we will try that approach, but we'll try to use the vector concept here to give us this area of the parallelogram here. Okay. Yeah. Okay. So let's look at this simple problem here. Okay. So I'm going to construct myself. Okay. By a typical way of calculating the parallelogram. So I'll drop B to A, and then to get the so-called height, right? Okay. So let's start with the very fundamental formula at here. Okay. So whenever you calculate the area of an object or area, so for this particular case, it will be the bottom length times the height. Right. So that's the direct formula you can use. Okay. So now let's look at what is the bottom length and what is the height at here, right? Bottom here is indicated by the vector A. So if I want to see the length, and all we need is to get the length of the A, right? Okay. And then the height at here. the height is the projection of B in the direction that is perpendicular to this A at here. Now if we already have the angle theta, then I can use the length B times the sine theta at here, right? Okay, so that's the height. Okay, so this quantity will be the height. Okay. Okay, so now you can already see that the area expression is absolute A times absolute B, and then times sine theta. So if you look at your notes, which is exactly the length part in the cross product definition, right? So I can rewrite this one here as this is basically means the absolute value of the cross product A cross B at here. Okay? Yeah. So that's how you would calculate the area of a parallelogram, okay, formed by A and B. Okay. To extend this a little bit here, okay, so let's consider a little bit special case here. Okay, so if I consider consider a two-dimensional scenario. Okay. Two-dimensional basically means your vector A will only have two components, right? And your vector B will also have only two components at here. Okay? Yeah. Now, if I substitute A at here, substitute B over here, okay, and then calculate the cross product, and then calculate the absolute value, okay, or the norm, okay, of this cross product, and then I was supposed to get area, right? Okay, so we can do a quick calculation at here using this formula. Okay. Area, as you probably understand, it's not a quantity that can be negative, but the determinant of a certain basically a certain vector or could be basically negative. So sometimes you can use absolute sign in here just to get rid of that negative sign here. Okay. Yeah. So what we can do now is we can plug in the formulas for cross product. Formula for cross product means it's ijk. Okay. For vector A at here, it's a1, a2. So the first thing here is, well, what do I do with the k components for the A? 0. That's right. So B at here, B1, B2, and 0. Okay. So that's the formula for the cross product. Okay. And then you can basically calculate the norm of this. Basically, once you get the vector, you calculate the norm or the absolute value of this vector. Okay. So we can try to calculate this, plugging. We don't have to use an actual number. We can use AB at here, the symbol, and you will see the results at here. Okay, is basically A1 B2 minus A2 B1. Okay, that's basically the results set here. And this results set here, okay, it's actually what? It's actually, if you put it into the matrix here, it's basically the determinant A, B. So in other words, maybe let's say put it this way here. Basically, this one here is A1, A2, B1, B2. Okay, so this one here essentially is this. Okay. And this is a 2 by 2 matrix determinant, basically, right? 2 by 2 matrix determinant. And I can, in this case here, I can shorten it. I can write it as this. So the first row here is A vector, and second row here is a B vector. And let's say if I just write it determinant A, B like this. Okay. So let's say if I say determinant bracket A, B, basically means we're gonna organize into a matrix. First row is A vector, second row is a B vector, and then calculate determinant, and then we get that number. Okay. Yeah. So just give you a different perspective. What's the area of parallelogram for A and B? Is this formula. If you have a two-dimensional scenario, then you can also see that the area of a parallelogram in two dimension, xy plane, is essentially the determinant of AB, a matrix formed by A and B. Right? So that's another way of looking at this parallelogram here. Okay? Yeah. So you'll see why I'm doing this one here, is because I want to make an analogy to the next topic here. Okay? So it's also related to the determinant. Okay? Any questions so far? Yes.
Yeah, but there's only still need the absolute.
Yeah, you still need the absolute. Yeah. So you really get if you really get a negative number, yeah, you still need the absolute value. Yeah. But sometimes it's also common sense. You don't have to really put absolute. You see an absolute, then you get rid of the negative sign, right? Yeah. Very good. Got? Okay. So let's look at the next topic here. Next scenario. Okay. Now we look at the area of a parallelogram, and then let's look at another geometry called. Let's look at the volume of a so-called parallelepiped. Volume of parallelepiped. What is the parallelepiped here? So let me do a drawing in it here. Okay. Suppose that we are given three vectors in 3D. Okay. So first vector, let's see, called A. Second vector B. And then C. Okay, so given basically means you know these vectors. Okay, so you have the quantity of all the A's and B's and the C's. Okay. Yeah. And now I'm going to draw the three vectors out. Okay, in a generic sense of in 3D. Okay, so let's say if the A, B, C are given such that like this. Okay, so let's say this is B here, and this is C, and this is A. Okay, so they are all pointing to different directions. Okay, pointing to different directions A, B, C. They are not. I purposely draw that they are not in the same plane. Okay, so now I can form an object using the three basically vectors that are here. So we can use the three vectors to form an object like this. So this is the object you can form. It's basically an object surrounded by parallelogram. Okay. So ABC. Okay, so to make it a few more information, to label a few more information in here, suppose the angle between B and C is theta, which actually probably don't really need that. Okay. Yeah. Okay. So now the question here is, what is the volume basically, right? What would be the volume of this parallelepiped? So this one here is called the parallelepiped here. Okay. So I'm going to use a very similar thinking as deriving this area of parallelogram. Okay. So if we're talking about the volume, okay, then in this particular case, okay, for a parallelepiped, and it's basically going to be the base area times the height. Okay. So that would be the straightforward formula for calculating a parallelepiped is base area times the height. Well, you might actually argue, so what is the base area? So in this case, so there are 6 sides, so you can use either side as a base area, right? And then the height will be basically, once you determine the base area, then you can determine the height. So in this particular case, let's say if I'm going to use the bottom here as the base area, then the height will be basically the shorter distance between the top and the bottom surfaces, right? Yeah. So I can draw something at here. So let's say if I draw a shorter distance, okay, so that will be the h at here. So that will be the height. Okay. Yeah. Is that good? Okay. Okay. So now let's proceed from here. Okay. Let's look at what is the base area and what is the height at here. Okay. Yeah. First of all, let's deal with the easy one. Base area. Base area is which area? Is this? This is happen to be what kind of shape? Parallelogram, and which we just learned. And the area parallelogram given by 2 vectors is basically what? B cross C. Okay, excellent, right? The absolute value of the vector B cross C. Okay, so the height is not as obvious as the base area, but let's try to use the idea that we actually learned, I just reviewed at the beginning of the lecture here, okay? Yeah. So basically I want you to think about how would you be able to obtain a height, an expression, first to obtain an expression of a height. So if this is the height A at here, what would be the alternative way of expressing the height now? The height could also be expressed as what? The projection of the vector A in which direction? That's right, right? So you can also say that the height is basically the projection of A in the direction that is perpendicular to the plane formed by B and C. Okay? That makes sense? Okay? So this seems to be complicating the problem, but if I write it in a mathematical expression, as we just reviewed at the beginning of the lecture, what's the projected length formula? You look at your review here. If I ask you a projected length quantity, how would you write it down? David?
The original minus the parallel?
That's one way, but there's another way. Right at the beginning. Projected length. This is an expression for the so-called projected length. Does that make sense? Remember this? So this one here, A dot B hat, is basically a different expression for the so-called projected length. What projected length? This is a projected length of A in which direction? In the B, right? Okay. So let's coming back to this one here. And we just said the height is the projected length of A in which direction? In the direction perpendicular to the plane formed by B and C. Well, I don't have a direction labeled here, but I guess I can always label a direction, isn't it? I can draw a direction that is perpendicular to B and C. So I'll call this direction as n hat. Is that okay? Right? So now I can write the height now. What do I write the height? According to the formula, it's what? A and then dot n hat. Does that make sense? Okay. So very good. So now my volume involves A, B, C, and then there's another one which is same, strange, different. That's n hat. So, but we do know what n hat is, right? N hat is a unit vector perpendicular to the plane formed by B and C. So next step, we just have to find out an expression for the n hat now, right? For the n hat. If you already have B and C, what will be an n hat? Or maybe ask this way: can you find a direction? Can you find a vector that is perpendicular to the plane formed by formed by B and C? What would be a vector that is perpendicular to the plane formed by B and C? I heard somebody, yes? Cross product, exactly, right? So cross product, if I can draw a cross product here, use a black color, so I can draw a cross product. So let's say cross product is what? B cross C, right? B cross C. So that's a vector perpendicular to the plane formed by B and C. Okay, so now you find a vector perpendicular to the plane now. How do you find the direction? N hat now. What do? You just have to normalize this vector, right? By its length. Okay? Yeah. Now that's n hat. Does that make sense? Yeah. So it's very logically, basically connect here for each step. Okay. It's not just a random, basically layout of expressions here. Okay. Yeah. And now I can make some simplifications here. So apparently I can actually cancel this with this. Okay. Then we end up with a very simple, okay, expression. So it's A cross A dot B cross C. Okay, so it's A dot B cross C. Make sure that the order really matters, and not A dot B cross C. It's A dot B cross C. Okay, so that's the volume. So technically speaking, you need an absolute sign in front of this whole expression because volume is also a positive number, right? Okay, yeah. So this one here is also called a triple scalar product. Okay, it's called triple scalar product. And the result headed here is derived by using the base area, which is formed by B and C headed here, right? So using the base area B and C. And you can imagine if you want to choose a different base area, you can choose maybe a base area formed by A and C, or you can use a base area formed by A and B. And then of course you will get the same volume, and expression wise it will be slightly different now. Okay, so the base area here is B and C. If I choose a different base area, then we might end up with, let's say, C dot A cross B, or using the other one would be B dot A cross C. Right? Okay. So same results, but just different ways of deriving it, right? Okay. Yeah. And one more step, just to compare with actually an analogy to the results I derived for the area parallelogram. And I want you can show, okay, so I'm going to skip a few steps here. You can see yourself. How can you show or prove, okay, the following? You can show or prove this following here. So this A dot B cross C, okay, so this formula that's which is representing the volume of this parallelepiped, is actually exactly the same as determinant A, B, C. Okay. So what is that? What does this quantity here means? If you think about the previous example, so this quantity here essentially means is A1, A2, B3, B1, B2, B3, C1, C2, C3. So that's the determinant. Okay. So you can try to prove you have ABC. How can you show the left side is same as the right side? It's quite simple. Basically, what's the right side? Calculate the determinant. What's the left side? Punching AB, okay, and then do the cross product, do the dot product, and you'll see the left and right end up the same thing. Okay. So essentially, now you can see the sort of an analogy here. The area has something to do with determinant for a special case 2 plane, and then for the volume for 3D, it also has something to do with this determinant concept here. Okay, ABC. You don't necessarily have to link to the determinant, but I just thought this is one way to show aside from the dry definition of a determinant, so you can actually relate that to the idea of a volume of the area, right? Okay. Yeah. Okay, so that's the area and that's the volume. I'm going to use the results that are here actually to do some derivations for the plane equations in 3D. Okay. Yeah. So before we move on here, let me ask you a quick question in here. Okay. Okay. So here's a quick question. Okay. So what happens if this vector A is actually in the same plane as B and C? Zero, exactly, right? So the volume becomes 0. Okay, and the idea is quite simple. Of course, there's 0 volume, but you can also relate to the linear algebra concept here. So volume is this, right? So this is a determinant AB, A1, A2, A3, and B and C's. Well, under what condition that this determinant is 0? Not forget about volume, right? Just think about linear algebra math concept. When you have a matrix whose determinant is 0, that basically means no, they're not necessarily 0. They have some values there, right? There is a concept. It's called linear independency, right? No. Yeah, yeah. So basically, if you have vectors all in the same plane, if this is A, B, C, okay, and you can always write your A to be a combination of B and C, or the other way around. C can be written as a combination of A and B, like that. So then the rows that are here, they are not independent anymore. So they're dependent, right? Yeah. If one row can be expressed as a combination of the other 2 rows, then the determinant must be 0. Okay. So that's just a side observation here. Okay. Yeah. All right. Good. So let's before we move on at here, okay, and let me ask you another question then. Okay. We look at the volume of the parallelepiped. If I ask you a even simpler type of object, okay, so B, C, and A here. So what we really want is actually red drawing here. Okay, so if I form ABC instead of parallelepiped, this is called a tetrahedron. Okay, so this is a tetrahedron in here. Right? And you can try to think of using the same approach, what will be the volume of this tetrahedron? So before you do a calculation, okay, take a wild guess. What's the percentage, or what's the fraction of this tetrahedron, the volume of tetrahedron, compared to the volume of the parallelepiped? 1/3? That's right. Somebody said actually the right number. 1/6. Who said that? Oh yeah, that's right. It's 1/6. Okay. Yeah. So it's actually 1/6 of the previous answer here. Okay. And I want you yourself to show it. Okay. To show that how it is 1/6 at here. Okay. Yeah. Okay, is that good? Okay, so if there's no question, this is basically, let's say, call it the end of the review of all the vector concept here. Okay, and then I'm gonna look at a completely new concept now from now on. Okay, so let's look at the plane equations, okay, in 3D. And then after this one, we'll look at line equations in 3D. All right. Okay. So let's lay down the problem at here, and then we'll try to find the solution. Okay. So let's say I have 3 points. So as you learned in the high school, when you have 3 points, it will uniquely determine a plane, right? So I'll just write down the 3 points here. So P1. Let's call it x1, x2, x3, sorry, x1, y1, z1, p2, x2, y2, z2, and p3, x3, y3, z3. Okay. So 3 points in 3D plane, in 3D space. Okay. I'll try to illustrate this out. So see that this is a P1, okay, then P2 at here, and P3 at here. Okay, so this is the known condition. I have 3 points, and 3 points will uniquely determine a plane. So maybe the plane we're looking for, okay, is like this. So in 3D, if you see a plane, it's basically there's no boundary. It's infinite, right? It'll go to infinite here and there, okay? Or it'll cut through the space, okay, and divide the space into half. Okay? So that's the plane that we're looking for. So what will be an equation to describe the plane? Okay. Basically formed by P1, P2, and P3. Okay. So whenever you talk about an equation, it's always about a general expression. So like a line equation in 2D, you know, it's y equal to kx, y equal to kx plus b, right? So involving a variable x and a y. So similar things, we really need a general equation involving, in this case now, involving x, y, z. So we'll start like this. Let's say suppose that I have another point P, okay, on the plane. So this point P has coordinates x, y, z. So we want an expression to describe this location x, y, z. And of course subject to this P1, P2, which is the condition in here to form the plane, right? Okay, so let's put a P point on this plane at here with coordinates x, y, z. Okay. Yeah. And I'm going to use the concept we just learned at here to derive this plane equation. So I will try to use a vector concept. So I'm going to form a few vectors at here. First vector I'll form is P1, P2. And the other vector form is take your time, snooze. Yeah. The other one will be P1, P3. Okay. And then I will have one more vector at here. So P1, P at here. Okay. So I'm going to form 3 vectors at here. So okay. So P1, P2, P1, P3, and then P1, P. As we learned in vector review, if you have your coordinates P1, P2, P3, you can calculate the vector P1, P2, P2, P1, P3 very easily. But just by using the coordinate of P2, subtract coordinates P1, or coordinate P3, subtract coordinate P1, then you get the actual vector P1, P2, P1, P3, right? And similarly for P1, P. And but then here, you actually think about it. You know, you basically will get x minus x1, y minus y1, and z minus z1. So you get x, y will be introduced right into this into the picture now. Okay. Yeah. Okay. So how do we relate all the information to the idea of the plane then, right? So we basically can use the results that we just derived from this volume for the parallelepiped. What is the volume parallelepiped? It's that A dot B cross C, right? And how was that parallelepiped was constructed? It was constructed using how many vectors? A, B, C. So how many vectors do I have here? 1, 2, 3, right? But only difference is all of the 3 vectors are in the same plane. So I can still imagine there is a parallelepiped formed by the 3 vectors, except that the volume of this parallelepiped is 0. And I can relate this to the formula that we just derived here. What is the formula? When we see the volume is 0, basically we see that the determinant of what? The 3 vectors, you put them together, right? Then you calculate the determinant of the 3 by 3 matrix. That's the 0. That's the results we just concluded. So basically in this case here, I have 3 vectors. Let's say suppose that this is your, I don't know how you can form, but it really doesn't matter. So you can P1P, this is one vector, P1P2, and P1P3. So this is 0, right? Okay. So I can see from previous results, okay, the determinant of these 3 things, you put them together into a matrix, you calculate the determinant, and this should be 0. Okay. So I don't want you to calculate this, right? But just think in your head. Thinking in your head basically means, okay, so how do I calculate this left side here? So calculate the left side basically means you need to get what the P1, P2 is, P1, P3 is, right? And you also need to get P1, P, which is this one. So then you need to do basically form a matrix by plugging the matrix at here. So the first one is here will be x minus x1, and this will be y minus y1, and this will be z minus z1, right? And then bottom here is these 2 vectors here. Okay. Then you calculate the determinant of these things. So last 2 rows are going to be some kind of constants, right? And the first row has x, y, z there. Then you calculate the constant. You apply that basically the formula for determinant of 3 by 3 matrix, and you expand everything. So in the end, you're going to end up with some sort of a function to do with f, to do with x, y, z. Does that make sense? Right? So you let it equal to 0. So you get the plane equation. Okay? Yeah. And if you are able to face that challenge, you can definitely try this out, and you'll get to the results. Okay? But that's not the way I will show you how to do it. Okay? This is definitely the way it is, but we'll just look at it slightly in a different angle. Okay, slightly different angle here. The volume is 0, meaning the determinant of this is 0. But if you recall, okay, when we look at the volume here, I use this side here, but I can certainly what? Use this side too, right? I certainly use this side. So I will try to use the other side, write it down here. Let's see. How does that help in terms of the computation? Okay. All right. So looking at a formula here. Okay. Just the same meaning, but just different formula for the volume formed by the three vectors. Okay. We can look at is this now. Okay, so P1P dot P1P2 cross P1P3. Okay. Yeah. So you can again you can think in your head. Okay, so I need to calculate the cross product of these vectors because these two vectors are all known, right? You can plug in, you get the constant. You can calculate these two vectors, and then you have this vector here, which is this one here. Okay, so you do the dot product, okay, and you will be able to get an expression, right? Yeah. So that will be the plane equation. Okay, but I think this is still a little bit too much computation here. Let's extend this from this expression slightly here. Okay. Now think about what is inside the bracket. It's a P1 P2 cross P1 P3, right? So if you look at the diagram here, what is the P1 P2 cross P1 P3? What does it represent? I mean, you first say is what? It's a cross product, right? And but the product, the cross product, meaning it's a vector, and it's a vector what? It's a vector perpendicular to this plane. Does that make sense? So I'm gonna just write it here. So P1 P2 cross P1 P3. Okay. Yeah. This is the vector. Let's call it n here. Okay. Let's call it n here. So now I can rewrite this as P1P dot n equal to 0. Yes. N just for now, just n here because this doesn't necessarily. This is n is a unit vector, right? Yeah. But this is a vector cross product, and it's definitely going to be a vector perpendicular to the plane, right? Okay. Okay. So basically, what I'm trying to shrink is the initial objective is to find the plane equation. Now it all shrinks down to one simple expression. It's P1P dot n equal to 0. So can you tell me what geometrically means when you have two vectors dot each other equal to 0? They're orthogonal, right? So any two vectors that are orthogonal to each other, the dot product must be 0. Okay. So here I have a P1P dot n. The n here is this guy here, right? The n is this guy equal to 0. Now if you think about it, if I choose a different n other than this, what does that mean? Am I still going to get 0? If I choose a different n other than this one here, but I'm still going to have to choose an n perpendicular to this plane here, okay? So let's see, illustrate this. If this is n here, okay, and this is another vector perpendicular to the same plane, what is the difference between these two vectors? 90 degrees? No. They're what? Just a magnitude difference, exactly, right? Magnitude difference, if this is n, if this is, let's say, n naught, whatever. So the n naught, when you see, they are just a magnitude difference. So this n naught are only different from the n by what? By a scale, right? By a scale. So literally, you can choose any vector n at here other than this cross product, right? You can choose any vector that is perpendicular to this plane at here. Does that make sense? Yeah? So now you can actually link this idea of the plane equation to this one here. Okay, so I'm going to write it a little bit more now. So I'll write it out. So this P1P is x minus x naught. Okay, I hat plus not x naught, x1, and then y minus y1 okay. So this is your P1P at here, and then this is n at here, right? So the physical meaning for the n at here is it's a vector perpendicular to the plane or normal to the plane that you're looking for. Does that make sense? Right? So the n at here, it's basically, this will be a normal vector to the plane. Okay. Any normal vector. Okay. Any. And of course, this cross product will be a candidate, right? It will be a candidate. Okay. So I will write this n at here. So I'll let this n equal to a, b, c. Okay. Because when you have a plane, you literally have infinite number of vectors perpendicular to this plane, right? And all of them are just be different by a scale. Okay. So I can call it A, B, C. Okay. So then the formula here now will become A, B, C equal to 0. Okay. So this guy dot this guy equal to 0. What's known, what's unknown? ABC will be a known quantity. It's a vector perpendicular to the plane. x1, y1, z1 is a point that was already given, that's on the plane. And x, y, z is a generic point on the plane. Okay? So now you can expand this calculation because it's so simple. It's just a dot product. So all you need to do is this times A plus this times B plus this times C and equal to 0. So you get A times x minus x1 plus B times y minus y1 plus C times z minus z1 equal to 0. Okay? So this is basically the plane equation we are looking for. Okay, this is basically the plane equation. And of course, you're going to have to firmly memorize what each one of these symbols here represents, right? So A, B, C. So let me rewrite it here. So this is basically, it's a vector, okay, perpendicular to the plane. x1, y1, z1 is a point on the plane. Okay. And you plug these two quantities, the n and x1, y1, z1 into this formula, and you get a plane. Right? So that's how you can get a plane equation here. So we'll emphasize a little more here. In order to get a plane, essentially you need to strive for two information. Number one, it's a point on the plane. Number two is what? It's a vector that is perpendicular to the plane. Okay? If you can find these two information, you will be able to construct the plane. Okay? So that's the idea. And for this equation and here, okay, and you can further expand it, okay, to have a slightly different format. If I expand it like this, I get ax, okay, minus ax1 plus by minus by1 cz cz1. Okay. And I'm going to move all the constants, okay, this ax1, by1, and cz1, move all the constants to one side of the equation here. And then I will call I'll call this big guy here as constant d. So now your plane equation will be looking like this now. Okay. So the first formula is actually I would recommend that you use the most. This is how you can construct a plane equation. And you can always simplify the plane equation into a format like this. Okay? Yeah. So we'll emphasize to look at this plane equation with a few exercises in the next lecture. Okay? And we'll look at the different scenarios. Okay? Any questions? Okay, see you on Thursday.